Hello students, welcome to another exciting lecture. I know, these are great, at least I think so. So the topic at hand now is heaps and priority queues. Let's get started. This content is from chapter 21 and obviously we're going to have examples and everything else, but let's get started now. We're going to discuss heaps from a conceptual framework standpoint. We'll explore how heaps are used to solve problems, how heaps are implemented, and then using heaps to implement priority queues, which are a specialized type of heap. A heap is a complete binary tree in which each element is less than or equal to or greater than or equal to both of its children. The first point on this slide actually defines a min heap, and there's also a max heap. So heaps have both structural and ordering constraints. And as with the binary search tree, we have many possible configurations for a heap given the set of elements the heap will contain. As I mentioned earlier, the first bulleted point on this slide is actually defining a min heap, and we'll also discuss max heap next. Both, actually. As promised, min heap has a root node as the minimum value. So the smallest value in this collection, in this structure, is the root node. The value of each node is equal to or greater than the value of its parent node. On the other hand, a max heap, the root node has the maximum value in the heap. So the value of each node is equal to or less than the value of its parent node, and then those become parents of nodes that are less than or equal to, the children are less than or equal to each parent, and vice versa for min heap. Here are the operations we're going to explore for heaps. Add element adds the given element to the heap. Remember, we have structural and ordering constraints. Remove min removes the minimum element in the heap, and find min returns a reference to the minimum element in the heap. And by this point in time, you probably could guess what the next topic is we were going to discuss. We have an interface for a heap ADT, abstract data type, and it extends the binary tree ADT. And there are the methods we just discussed: add element, remove min, and find min. As mentioned on the previous slide and described in this UML diagram, the heap ADT interface extends the binary tree ADT. Here we show two min heaps which actually contain the same data with different ordering, and they both adhere to the protocol of a min heap. Each node is less than the children, less than or equal to the children. For us to add an element to a heap, we first add the element as a leaf, keeping the tree complete. However, then we must move the element towards the root, up towards the root, exchanging positions with its parent until the relationship among the elements is appropriate. This guarantees the resulting tree, after all this is done, will conform to the heap criteria, i.e. min heap or max heap. Now I'm going to walk you through a graphic depiction of inserting or adding a new element to an existing heap. So, and we have two examples of heaps, one on the left, one on the right, obviously. And so we see the only possible insertion point for the tree on the left and the obvious insertion point for the tree on the right. Now remember, we insert the element without first caring about its value. That's part 2 of this process. So in the example that was on the left, we're going to insert the 2 as a leaf whose parent will be 4. And then, since 2 is obviously a min heap, since 2 is less than its parent, those 2 will be swapped. And then 2 becomes a child of the root node 3, but because 2 is less than the value stored in the root node, 2 will be swapped with the root node, and then 2 ultimately becomes the root node of the resulting tree. Heap, sorry. It's been a long day. Next, I'm going to walk you through the second operation, which is removing the min element. And obviously we're going to have, well, not obviously, but rest assured we're going to have a graphic depiction of this showing the steps. We're going to remove the root, okay, which is the min, obviously min heap, and then we'll reconstruct the heap. So first we'll move the last leaf of the tree to be the new root of the tree. Then we'll move it down the tree as needed until the relationships among the elements is appropriate. Most particularly, we'll compare the element to the smaller of its children and swap them if the child is smaller. Here we see 3 state snapshots of the process to remove the min element, which is the root element. So the 3, obviously it's a min heap. The 3 will be removed. It'll be replaced with the 9. And then 9 will be compared to 4 and 5. 4 is the lower of the 2, and 9 will be moved down 1 level, but that level has no children. So it will be a min heap reordering. It meets the criteria. So please recall that queues use the FIFO protocol. They remove elements in the order in which they were added. First in, first out. A priority queue removes elements in priority order, which means that's independent of the order in which they were added. So a priority queue does not use the FIFO protocol. And priority queues are very helpful in scheduling, many scheduling situations. And a heap is the ideal mechanism for implementing a priority queue. Before we start looking at the implementation details, I want to walk you through a sample program. This is from the driver. I've got a priority queue already created, and we're adding some elements in this order. And I put a breakpoint on the second call to the add element method. So that has not been executed yet. So all we've added is an element. The string is Aranola, and its priority is 99. So I'm going to now take you to the next slide, where we're going to look at the memory state snapshot of this program running with that breakpoint active. On the left, you see the sequence in which these elements are going to be added to the priority queue. But at this point in time, the only one that has been added is Aaron Nola with a priority of 99. And we're taking a look at the underlying structure that holds this. And you'll see element number 0, which is a prioritized object. We'll get to that in a second. Has a priority 99, arrival order of 0, and the element string variable is Aaron Nola. And you could see the other elements are null. And oh, by the way, next order is 1. It gets bumped each time we add a new element. It gets incremented by 1. Okay, now I've proceeded to step over the second add element, a call to add element, in which we added the element Didi Gregorius with a priority of 1. Now take a look at the order of the elements in the priority queue. You could see Didi Gregorius is now priority 1. Its arrival order was 1 compared to the arrival order of Aaron Nola, which was 0. But look where it is in the tree. Now I'm going to attempt to walk you through adding more elements to the queue with different priorities live. So the next element we're going to add is Charles Jones 50. Okay, now if I come down here, element 0, Didi Gregorius, 1, Aaron Nola, Charles Jones. Now I added Juan Soto, and guess what? Juan Soto has a priority of 92, and now it's on the right. So Aaron Nola was pushed down. Next we'll add Mookie Betts. Juan Soto is down. Aaron Nola is down. Charles Johnson is down. And now Mookie Betts is in place. I'll add the last element, which was Albert Pujols. There we see Albert Pujols. And now we're going to print them. We're going to use the remove next element to print these. I've been setting up this slide for about 15 minutes and my phone is ringing in the other room. I hope that's not too much of a distraction, because I'm just going to keep on going. And we'll blame it on the pandemic, which is when I'm recording these slides. So now go to my output, Didi Gregorius, Mookie Betts, Charles Jones, Albert Pujols, Juan Soto, and Aaron Nola. print it out by their priority. Hope this was useful. Now let's pull this all together. On this slide, you see on the left the list of elements added to the priority queue in the order in which I added them. It's the element, the string element, and its priority. Aaron Nola 99, Didi Gregorius 1, Charles Jones 50, Juan Soto 92, Mookie Betts 10, Albert Pujols 55. And then at the top of the slide, you see the code after all of the PQ dot add elements finished executing, the code which will walk through removing the elements in the queue using the remove next method and printing them. And you could see the order in which they're removed and thus printed. Didi Gregorius 1, Mookie Betts 2, Charles Jones 3, Albert Pujols 4, Juan Soto 5, Aaron Nola 5th. 1, 2, 3, 6. Sorry, lost count there. So you get the idea of how a priority queue, you should get the idea of how a priority queue works based upon this demonstration. I'll put the code in Canvas. You obviously have to import that code, run it, walk through this, and see the mechanics of this very important data structure. One last thing I want to cover is the prioritized object class, which implements the comparable class, which gives us the ability to compare. It creates a comparable object out of a prioritized object, which gives us the ability to compare the elements. And it gives us these methods: compare to, get arrival, order, get element, get priority, to string. I want you to take a close look at this. This is just, we've used comparable before in the past, so I need you to revisit its implementation and then apply that and see how it's applied here to this data type. You might have guessed, next we'll look at implementing heaps with linked nodes. And the operation on a heap, or the operations on a heap, require moving up the heap as well as down. So we're going to add a parent pointer to the heap node class, which is based on the node for a binary tree. In the heap, we're going to have to keep track of a pointer so that we always know where the last leaf was or is. Now we're going to take a look at a live demo of a linked heap, link-based heap, I should say. So I'm going to just run it and demonstrate. And this is an assignment, by the way. Oh, assignment announcement. This is it. This is your linked heap assignment. So you're going to replicate what I have here. I'm going to give you some starter files, but there's quite a few things you're going to have to change. And in order to make those changes, you're going to have to understand the underlying structure of the linked heap in order to make this work. So this adds people's names, and it stores them last comma first. So let's start off with, I'm going to add Mike Schmidt. I'm going to add, I don't know, Bryce Harper. I'm going to add Steve Carlton. So now Mike Schmidt's going to be the root because that's the first one I added, and then these others are going to be distributed throughout the linked heap. So let's talk about some of the deliverables. Well, what do you think the height of this is right now? This is a method you're going to code and add to the user interface. I do have a breakpoint here, and we'll just continue to go. The current depth or height of the heap is 2. Okay, and if I go to list, okay, here's how it's going to list them. Root followed by the children. If these are roots with other children, that'll come next. So let's add a couple more names. Let's add JT Real Muto. Let's add DD Gregorius. Now, if I were to list now, okay, you've got your root, Mike Schmidt, and you've got Bryce Harper and his children. And then you've got Steve Carlton with no children. So if I add another element to this, we'll say Bob Boone. If you're a Phillies fan, you probably don't remember him because you're too young. So now, if we list these, pain in the neck. Okay, so what we have now is the root, Bryce Harper, and he's another binary tree node with 2 children, JT Real Muto, DD Gregorius. Steve Carlton is another node. We has Bob Boone and an empty slot because this is a potential leaf right here that is empty. So what do you think the height of this would be? Well, Schmidt, Harper, Carlton, that's 2. And it should be 3, right? So let's try. See what the height is. Of course, I've got breakpoints. The depth of the heap is 3. Now this is getting really long, so I'm not going to be able to continue this demo. I'm going to stop. Get to where I'm going to stop now. And then I'll do another demo. I'll bring it back up. Let's call this the factory tour. I just ran the program, adding quite a few elements to the heap, and I took this output dialog and I copied it into the assignment um, instructions and the text at the front. And now what I'm going to do is I'm going to walk you through some of the things that needed to be added. Um, in the link binary tree, is empty, I believe, needs some work. Get root element is going to be a problem. Get height is going to be a problem for you. I don't believe toString was coded. No, that was not coded. That's going to be a problem for you. And the code, when I give it to you, when you remove the last element from the heap, it throws an exception, and you need to fix that. I could show you that kind of right now if you want. I'll just run this. So when you get this, let's just add a couple names. So I've got, if I list this, it's just going to show me the root and its two children, and the size or the height, depth, whatever you want to call it, is 2. It's a full binary tree. So if I remove, it's going to remove the root, then it's going to remove Carlton, then it's going to remove Schmidt. And if you try to remove this the way I give it to you from the textbook, it's going to throw an exception. You need to fix that. There's no reason to throw an exception. Just report back that it's null. So yeah, this project is going to require you to look under the hood of this thing and really see how this linked heap is working. And it's going to be, I believe, challenging for some of you, maybe all of you, to get this working. So I would not leave this till the very end. I would start working on this immediately. Hey, thanks for watching. Next up is a heap implemented with an array. Since a heap is a complete tree, it's totally plausible, reasonable to implement it with an array as its base. So as we discussed earlier, in using an array, the parent at index n will store, the children will be stored at index 2n plus 1 and 2n plus 2 in the array. Conversely, any node other than the root, the parent of the node is found at index n minus 1 divided by 2. So it's pretty simple, straightforward. What I'm going to do is just demonstrate an array-based heap next, because we've got lots of topics left to go and we're running out of time. I feel like we're running out of time. So I'm just going to give you a quick demo next. Now we're going to take a look at an array-based heap, and we're going to implement a max heap as depicted in this diagram. You can see the initial values in the array: 1, 3, 5, 4, 6, 13, 10, 9, 8, 15, and 17, and the corresponding max heap structure. So before we look at a program that implements a heap with an array, let's take a look at a snapshot of a run from that program. So the input array was 1, 3, 5, 4, 6, 13, 10. in indexes 0 through 10. N is 11 in this case. So a parent element at index n will have children stored at index 2n plus 1. So let's just take 17. 17 is an index 0. So 2 times 0, 0 plus 1 will be index 1. There's the 15. And then 2 times 0 plus 2 is going to be 0 plus 2. There's the 13. Correct. Now let's take 15 as a parent. 15 is at 1. 2 times 1 is 2, plus 1 is 3. And there is 0, 1, 2, 3. There's the 9. And next to it is the 6. And you can continue doing this calculation all along the way. And this is how the array is reconfigured to store, in this case, a max heap. Now we'll take a quick look at the program I put together for this heap, and I have it running, and you could see the components. We start off initializing an array with those values that I used in the slide. We capture its length in an integer. I do print the array, print the heap first, the array. And then we call the method build heap, which basically identifies the last non-leaf node as being stored at n divided by 2 minus 1. We went over this math already. And then we perform a reverse level order traversal from the last non-leaf node and heapify each node. So, and heapify does a lot of the work. Here's the math that we talked about. We declare a variable largest, which initializes the largest as the root. Then the left is 2 times I plus 1, and the right is 2 times I plus 2, which is where the children of each parent will be stored in the array-based heap. And it calculates which is the right child and which is the left child, and then it recursively calls itself. And so if I were to run this, where's my output here? Here's the original array representation. And there it is, as represented by the heap. And if you use that math, 17, if you go back to that slide, 17, which is index 0, will have children 15 and 13, 9. You get it. You get it. This is pretty straightforward. I'll put this in the timeline in Canvas so that you can take a look at it and walk through it. At this point in time, I don't think I should have to step through a program in a video, since I'm going to give it to you. It's somewhat natural to think of a heap as something we could use to sort a list of numbers, since it has such a nice ordering property, max and min. So we have what's called a heap sort, which sorts a set of elements by adding each one to a heap and then removing them one at a time. And the smallest element comes off the heap first, so the sequence is going to be in ascending order. Here is the source code. I'm sorry, the Yeah, the source code for the public class heap sort that implements the generic data type T. And in the example I have, we're going to use a contact list, an object that contains, I believe it's last name, first name, and, well, we'll see in a second. There's some other element, I can't recall. So we create an array heap named temp. We copy the array into a heap using the add element method, and we take each element from index 0 up through the length -1 and copy them to a heap or add them to a heap. And as we're doing the add element calls heapify, add heapify, I believe is the method. Heapify add, maybe we'll take a look in a second, and it puts them into the heap in the order necessary, and then we remove them minimum first and add them back to the array. So let me walk you through this implementation of a heap sort. We'll start off with the main and what types of objects are going to be added to the heap and sorted. We have this contact class, which basically creates an object with first name, last name, and a phone, which is a string. I remember it being numeric, but it's actually stored as a string. And so we're going to create this new contact list, and we're going to add these contacts manually, if you will. John Smith, Sarah Barnes, Mark Riley, Laura Getz. You should know that the contact class implements comparable, so we'll be able to compare all these. And then we have our heap sort, which it's not very complex. It's going to create a new array heap. It's going to copy the array into the heap using add element, and let's take a look at add element calls heapify add, which adds these per the protocol of a heap. And so we're going to add them to a heap. They'll be stored using that ordering protocol. And then what we will do at the very end is first we copy the array onto a heap using heapify add and add element, which calls heapify add. And then we will place the sorted elements back into the array by calling the remove min heap and placing the minimum at data sub 0, and we'll keep on going until the heap is empty. If I run this, you'll see that the list is now stored back in the array, and we have Sarah Barnes, Laura Getz, Marcia Grant, Frank Phelps. So they're in ascending alphabetic or sorted order by last name. And now we are done this chapter. I wanted to put this in there. It's really important material. I hope we didn't go too fast. Thanks for watching. Have a great day.